Welcome back to the EXD. By the end of today's episode, you will have a high-level sense of the architecture of this LLM. You will actually be able to say, okay, these are the high-level steps involved in producing artificial intelligence of the LLM variety. Because in this episode, we are finally going to start doing some brain surgery, or more accurately, brain scanning of the Qwen 3.6-35B-A3B. Congratulations for having made it so far, because now we're going to get serious. My name is Ram, and this is an open learning log that I call the EXD. To start at the beginning, check out episode 1. I'll link it in the description below. Okay, let's start. First, a very quick recap on the way of the EXD. At the EXD, we learn about LLMs from the outside in. So, unlike most traditional learning programs where you start with neurons and simple perceptrons and build up towards more and more complex architectures, in the EXD, we start with a cutting-edge model like the Qwen 3.6 that we're looking at now from the beginning. And we peel that onion layer by layer to understand how the parts inside work. So you don't kind of have this long slog from the base fundamentals all the way up to the cool stuff that we want to play around with. So in the last few episodes, and please go check them out if you're seeing this for the first time, we started right at the top and we peeled the first onion to see what the anatomy of an LLM inference pass looked like. And we understood at that very high level there are these three stages. You take a text input, you tokenize it, and then it goes through a prefill stage, then a decode loop, and finally you get your answer. Today we're going to peel the next level of this onion. So it's kind of like we're somewhere here on the outside and we're peeling one more level. It's not all the way in, but we're going to start seeing some complicated stuff. It still is a pretty high level picture of these things. These are the most complex things humans have ever made. So we have to be patient. We're going to peel this layer by layer. So we were here, and last week we understood what tokenization is. This week we're going to peel one more layer and start looking at this process like this. We're actually going to take a look at the high level architecture of the model, and we'll get into it. This week also starts, the EXD is going to start being hosted on Hugging Face, so I'm going to actually narrate this from a Hugging Face article. I'll link the Hugging Face below in the description as well. But don't expect deep dives into these boxes. Each of these things, we've kind of done a deep dive on the left side. You recognize the BP tokenizer, which you saw last episode, what embeddings are, etc. This episode, we're not actually going to dive into the boxes. We're just going to describe what the boxes are at a high level. So you first get a lay of the land at a very high level. And then over many episodes, we're actually going to dive in and start turning screws, opening panels, and start looking at the stuff inside. Okay, so let's get to it. This is my Hugging Face page. I will link it below, and I'm going to start documenting all of this, the EXD journey over here. This is our architecture overview article. And like always, I have a little simulator ready, so we can actually click through and understand what each of these pieces are at a very high level. And that's what we'll do. And in further episodes, maybe we'll start diving in and getting into some really deep, cool stuff. Okay. This episode, it's going to be all about the high level. Let's go back to the article. Okay. So the Qwen 3.6 3.6-35B-A3B model is a hybrid mixture of experts model. Okay, the 35B means it has 35 billion total parameters, and A3B means only 3 billion of these are active per token. Okay, so it's like you've got 30 billion parameters, but a token or a query that's passing through this model is not hitting all of them at one time. At any given point, only 3 billion of these are hit, and this is obviously for computational reasons. These numbers are actually going to start making a lot of sense to us over the next couple of episodes, and we're really beginning to understand what all of these are. Today, you're going to get a sense of what these numbers mean. So, like we said, we have 35 billion total parameters, 3 billion active parameters. We have 2048 hidden dimensions. We've got 40 layers. 30 of these are gated delta nets, and 10 of these are full attention heads. We'll understand what all these numbers are slowly, bit by bit. It's a lot of complicated stuff. I'm learning about this as I create these episodes, so we'll proceed slowly and steadily. Okay. So if you look at this, you'll see that there are 3 stages. You have the input stage. This is the transformer stage, but it has 40 blocks. So this stage has 40 blocks, all of which look like this. And then finally there's an output stage where the next token is actually determined. So this is where all the thinking happens, and then there's a little bit of, you can think of it as like formatting or finalizing the answer, and then the next token pops out. Let's go through this one by one. Okay? So we saw this. We know from last episode that the input tokens are from a vocabulary of these many possible tokens. There are some special tokens involved as well. Your text is actually split into tokens by a BP tokenizer. So basically all the text in English or other languages that this model speaks can actually be represented by this vocabulary of 248,000 odd words. And in fact, tokens, and these tokens are often subwords. So multiple tokens can join together to form a word. And these tokens are actually represented inside a 2048 dimensional space. Okay, so just like we have 2-dimensional spaces, 3-dimensional spaces that we live in, we have a 2048 dimensional embedding space, and every token is a vector inside that embedding space. Okay, we covered all of this in our last episode, and we foreshadowed something called positional embeddings, where these tokens are actually predetermined. It doesn't get determined at runtime. We actually simply have a dictionary that says, okay, token for cat is represented by this vector. And we did one thing last episode where we said, hey, if you have the cat sat on the mat, or the mat is on the cat and the mat positions matter a little bit. Like man bites dog, dog bites man, completely changes the meaning of the sentence. So there is a small step that's performed that just modifies this vector a little bit to sort of give the LLM a notion of where it is present in the query, okay, before it is actually fed into what is kind of, you can maybe think of this as the frontal cortex of the LLM. And we'll discuss that in the next episode. Okay, so this is the input stage. Let's just go through it. So we have the tokenizer, we have the embedding lookup, and then we have the positional embedding. We will dive into this deeper, and we have already covered this in the last 2 episodes. The next stage, once we do this, right? We understand what the boxes do. Actually, let's just go over it again, just to set the tone for the rest of the episode. What we're trying to do is understand what each of these boxes does at a high level. So we won't understand it perfectly, we'll just get a sense, a sort of feel for what it is before proceeding. So these are the input tokens, that's what these boxes are. They have been produced by looking up your text and seeing which tokens represent your text. That's what happens in this box. These two boxes actually. Then those tokens are represented as vectors inside an embedding space, and all of those vectors are then adjusted a tiny bit, in this case rotationally, to represent their relative positions inside the query. That is what has happened at a high level inside these boxes, and now they're ready to be thought about. And we enter the infamous transformer block. This has been the most successful architecture for LLMs, the transformer architecture, and we're going to see a lot of this in the coming episodes. And it's really worth understanding how this beast works. Okay, so let's look at it. There's a lot of numbers here. We know there are 40 blocks that look like this. There's some other numbers here. 30 of them are GDNs, 10 of them are full. We'll understand what all of that means. Stage 2. So stage 2 is basically the transformer is composed of 40 identical transformer blocks, and this is what they look like. The RMS norm block, an attention mixture, a residual connection, another RMS normalizer, and then the mixture of experts feed-forward network, and then another residual connection. So that's sort of a very high-level picture, and you can see that here as well. There's RMS norm, attention, RMS norm, MOE, and actually this dotted line, which is not rendered so wonderfully, is actually showing the residual connections. Okay. Let's talk about the RMS norm first, because it's very simple. The idea is just to normalize the vector sizes. Okay, it's a simple root mean square normalization, which is applied to the vectors before it goes into the attention network. Now we're going to do a lot of math on these things, and one of the things we want to do is just it's kind of like just making sure everything is of a reasonable size, like all the vectors, before we go in and start multiplying things so that they don't go kind of out of bounds. That's what you generally do with normalization. It's a way of like fitting everything into a neat and manageable band. So each and every token is normalized with a very simple RMS normalization, and also a gamma, where this is actually a learned vector. As part of the training process, there is a learning. So it's a small parameter set which actually is applied to the RMS norm. We're not going to talk about how training happens. This is the forward pass in inference. We'll get a sense for this and then understand. It's kind of like we'll understand how the engine works, and then only once or the engine runs, and only after understanding how an engine runs do we then think about, okay, how do we design engines? So we're not going to really talk about how gamma is earned, but we basically say this is what this does. You can think of it as taking all the input token vectors, which might be, kind of like this ball of vectors pointing all over the place. We're going to just squeeze them and kind of just bring them all into a nice band, which will then pass through the attention network. Okay, that's this box. Okay, then it goes into the attention box, and remember there are 40 layers, and it actually, depending on which layer it is, there are two different types of these. Okay, so 30 of these layers use gated delta net, and 10 of them use full attention. So 1, 2, 3 will be gated delta net, 4 will be full attention. Then 5, 6, 7 will be gated delta net, 8 will be full attention. What does all this mean? At a high level, what we're saying is beyond the position of a token inside a query, the tokens inside a query also have a certain relationship with each other. So if you look at a sentence like a man sat next to a cat and petted it, the word "it" relates to the word cat. It references cat. It does not reference man. So beyond just the fact that it is at the end of the query, there's also an extra piece of information that it is kind of attends to the token representing cat more than, say, like in a certain way. And it also attends to the token representing man, but maybe it doesn't really attend to in the same way. So we want a way to represent the interrelationships between all the tokens in the query, and that is what we call attention. Okay, this was the huge breakthrough from Google, which in the famous "attention is all we need" paper, which kind of unlocked a new level of performance in LLMs. Okay, so that is what this attention block does. Let's go back here. I'll just run through it so in simple English so we kind of get a sense of what's happening. We take text and we split it into tokens. We take those tokens and we represent them as vectors inside an embedding space. Then we sort of rotate those vectors slightly to represent each of those vectors' position inside the query. Then we normalize those tokens so that they all sort of fit neatly in a nice, comfortable band that we're now going to perform operations on. And then we do this pass where we say, hey, here's this collection of tokens, but this token, which represents it, is kind of closely related to this token that represents cat. And we're going to build actually a set of connections between the tokens. Once we do that, that's what attention does. Now, if you think about a query that's 1,000 tokens long, if you have to do it for each token, that would be 1,000 squared operations, right? Because the first token, you need to compute its attention for all the other 1,000 tokens. Then the next one, well, 999, but you know what I mean. Then the next one, and you have to do that operation 1,000 times, right? So this grows quadratically with the query size. So if I have 2 input queries, then I have to do 4 attention kind of operations. But if I have 10 attention tokens, I have to do 100. And if I have 100 attention tokens, I'm now in 10,000. So this grows very rapidly with the size of the query. So to solve this, they actually invent what Qwen does, and the goal of this model is to be a faster model, is it has something called a gated delta net attention layer, which does not pay attention to the entire layer, but kind of has a way of like reducing that cost. What it basically does is it keeps kind of a running summary of the query instead of paying full attention to every single token. But every 4th token, you in fact do full attention, and you actually compute the attention of every token with all the other tokens that are there. Okay? So we don't need to understand this perfectly right now. Let's understand this at a high level. What we're doing at the attention step is we're saying, here are the tokens, here are the vectors represented by those tokens, here are those tokens adjusted for just pure position in the query. Now, here is a sense of which tokens are related to which other tokens. Okay? That's what we're doing in this attention layer. Once we do that, we have performed a series of operations on things now, so it makes sense to do a kind of normalization again, because maybe in the computations we have done, things may have grown or become short. So we sort of normalize all those vectors, and then we feed it to the router. And what the router does is it basically, this is where the term mixture of experts comes from. It routes in each pass, it selects the top 8 experts for each token from a total of 256 experts in some complicated way that we will understand later. And then only those 8 experts actually work on your query to produce a next token, okay? Or at least in this gate, in this layer. This is how it achieves the A3B. It doesn't run it through all 256 experts. Your model is split into 256 experts. At any given time, only 8 of those experts are active. And this is how you get a mixture of experts model. Okay? This is detailed over here. And this is important to understand. Each layer has exactly the same structure. Okay? And we'll dig into the complexity of how all of this works in future episodes. At this level, in this episode, we're staying at a very high level and just understanding sort of the function of each of those boxes. So the function of this box that we're looking at right now, which is the MOE feed forward box, what we're doing is we're taking these tokens, we're selecting 8 out of 256 experts and giving it the query vectors to work on. And this passes through 40 such layers. So the first layer, gated delta net, 8 experts, RMS norm, goes through. Then RMS norm, gated delta net, RMS norm, top 8 experts. RMS norm, the third layer, RMS norm, gated delta net, RMS norm, top 8 experts. And when it hits the 4th layer of these 40 transformer blocks, we get RMS norm, and then we do full attention, and we actually compute the attention of every single token with every other token. Then we do RMS norm, and then we go and hit the top 8 of 256 experts again. And it goes through this process 40 times. Okay? It's totally fine that we don't understand how the hell this produces intelligence. But before we can understand that, we should know what the different pieces are, right? We need to know, okay, this is the carburetor, that is the fuel supply, this is an ignition, this is a spark plug, those are the pistons, this is the axle. Before we can understand that functionality, we need to know what the pieces are. That's what we're doing in this episode. Okay, cool. So we're through with the transformer block, 40 of these blocks. And we pop out to the output block. So after the 40th transform block, we do a final normalization, and then it goes through what's called the LM head. And here you'll notice that it's a projection from 2048 dimensions to 248,320, which, if you remember, is our vocabulary size. So what actually this step does is it pushes out what are called logits. Logits, a way to think about it is just the odds of saying, hey, I think the next token is, so imagine the 248,320 tokens. We're basically saying, I think these are the odds that this is the token that should be next. These are the odds that I think the next token should be next. These are the odds that I think the next token should be next. And obviously, only some of them will be highly likely, while the rest will be extremely unlikely, right? That's what happens actually here. This is where those numbers finally get produced. And then we have a sampling strategy where we decide which of those based on these logits we pick. And then this bit is, we looked at it before speculative decoding, we'll just ignore that from now, okay? So let's go over this one more time on the sort of diagram before stopping. So the final RMS norm is just a normalization that's applied, and whatever came out of this, your query has gone through all these calculations and popped out as a new set of vectors, is then passed to this head where it finally projects odds for every singular character in the vocabulary space, saying most likely, these are the odds that it's A, these are the odds that it's B, these are the odds that it's C, these are the odds that it's cat, these are the odds that it's dog, these are the odds, and it just produces it for literally every single character. And here, this will give you a clue. This is one of the reasons why we can do MTP in one pass, on multiple things, but we'll get back to that later. And in the next token, you basically, so that's what happens here. So this step produces the raw logits of the vocabulary. And then finally, the next token is sampled from this probability distribution over the vocabulary, and the next token is finally returned. Okay, this was obviously a lot to hold, to understand in one session. So please, after this episode, check out my page. I'm going to link it below. You will have to walk through this a couple of times, step by step, to see what it looks like. You can, both the space that I showed you and the article are on my Hugging Face page. You can see them right here, and you can see all the steps. You can click through them and read about them to get a sense of what each step is. And I think that is actually a good place to end this video. We did a whirlwind tour of the big chunks. What are the pieces that make this engine in this episode? Tomorrow, we're going to start with MROPE. Oh, sorry, not tomorrow, in the next episode. And start understanding how each of these boxes work. All right. So I think that's a good place to end today's episode. See you guys next week in part 2.